Everyone. In this session, we will look at reinforcement learning, and on the lecture, we will take rather more superficial view of different algorithms on the reinforcement learning. And then later on, it will be followed up by discussion of case studies in terms of robot motion planning using reinforcement learning algorithms. And that time, we will to dive into further details or the mathematical aspect of individual algorithm. Now, this reinforcement learning, it may be or it may seem a bit new or to the community in robotics or the community of computing, but reinforcement learning on its own has been very highly investigated by pedagogists or animal psychologists because our brain is often an inductive learner, and psychologists, they often try to teach animals to undertake tasks by giving them positive or negative rewards, or as the kids are also grow up, if we look at the context of pedagogy, that sometimes even unconsciously we give some sort of reward to the kid, or sometimes we scold the kid in the school. Maybe I will also do it to you, to give them positive and negative reward to indicate them what is good, what is bad, because in philosophical sense also it's many times it's dubious that what is good, what is bad. So I cannot tell in abstract term or very explicit terms, so rather we give some indication. So in the rest part of the lecture, we will see that how we can mathematically encode that and teach a machine in similar way. And later on, we will make it far closer to human learning when we will talk about imitation learning. Moving on. In the next hour or so, we'll first look at the introduction more from a mathematical point of view, or contextualize it with other machine learning techniques, that how reinforcement learning is different or similar to supervised or unsupervised learning. On the very first class, we had a very brief discussion on different types of machine learning. And then we will learn about three types of passive reinforcement learning algorithm. And in this case, I will mostly follow the notation of the book by Russell Novick, A Modern Approach to Artificial Intelligence. It's here. And then we will have a comparison of these three algorithms: the direct utility estimation, adaptive dynamic programming, shortened as ADP, and temporal difference learning. And after that, we will go into the active reinforcement learning. So in subsequently, I will discuss the difference between the passive and active reinforcement learning. And we will learn about Q-learning and multi-arm bandit problem, which is a very well-known problem. And it will be followed up by discussion of some case studies where our students developed scheduling algorithm using the concept of multi-arm bandit problem. And finally, we will very briefly introduce you with some advanced reinforcement learning concepts like the deep Q learning, which you may find some resemblance with the direct utility estimation when we will discuss. Then inverse reinforcement learning, mainly one of my PhD students, Mukund, he is doing PhD on imitation learning. So he will take a session on inverse reinforcement learning and its applications to mixed reality interfaces and for human robot handover request. And of course, we will show you demonstrations. And during that time, we will go into further detail on explaining the algorithms. So in terms of mathematical introduction, that when we looked at supervised, unsupervised learning, we talk about that in one case, we have training samples. In another case, we do not have training sample. And in reinforcement learning, the algorithms will be explained in a context that where there will be an agent. So in a motion planning class, you can consider the agent is being a robot, like a moving bot or a fixed base bot, or maybe a flying bot like a drone. Or it is not confined to a physical agent. The agent can be also a software agent, like when, say, we are developing a virtual game player for a game. And then there will be an environment. We will go into further details that how we encode environment or what its effects on the algorithm in subsequent slides. But this agent will act on the environment And based on this action, the environment will respond back, and the agent will perceive this. If you uh, briefly remember that in the MDP lecture, we indeed discussed about this cognitive model, and in turn, the agent will perceive this new state, and also it will get some sort of reward, which will be an indication to that how good is the action or how near it is to the goal state. So the goal will be a function on the state fx equal to y, and the data will be in the form of x1, y1, something like that, where y is the reward. Here, what we will try, which is very similar to our value iteration or policy iteration algorithm that we discussed earlier, that we try to maximize the reward for a pair of state and action. And the data will be given in the form of this reward and state. So unlike as we discussed during the value and policy iteration class, that we will not know the model or the state transition probability matrix. Rather, we will be given data as the agent is perceiving the environment, and we will try to maximize the reward. And of course, the ultimate aim will be to go to the goal state. In some cases, we will try to take it near to the goal state when the goal state is not very well known. So if we just look back the examples of this supervised learning and unsupervised learning, that in supervised learning, the training data we get in the terms of observation measurements, and we know that what we want to get out of it. So we train a model, and the main trouble here is that often our observation or measurements that has some inherent error, either due to the measurement accuracy or transmission accuracy, or maybe for many other reasons. And we try to fit a model where we can minimize that error. But we know that what we want to get. In unsupervised learning or clustering, the class levels of data are of course unknown. So we have the data, and based on the distance metric among the data, we try to segregate the data. And the distance is measured based on a set of features of the data. In case of reinforcement learning, that we get the best reward or the goal when we get the +1 or -1 reward once we reach the goal state. So at the present, like the supervised learning, we do not immediately get the benefit of our action. We give some indication in the form of reward, but that is just an indication. That is not the final reward. And the agent itself chooses training data. So in a few slides, you will see the example that how the agent creates that as the agent move across the environment, based on its movement, it creates the training data. So it is not separately given. And that is one huge benefit of reinforcement learning, that we need not to bother about collect a set of big data and then we will train our model, unlike in supervised learning. Or it is not like that we only have the data and we have to segregate the data like clustering. Rather, we can generate our own training data, and based on that, we can sense the environment and choose what to do. And then it will sound a bit philosophical, this explore versus exploit, and we will see the mathematical formulation of that when we will discuss this Multi-arm bandit problem. That this explore versus exploit is that if you look at our everyday life also, and in that we can do whatever we were doing before. But then we all do that, let's do something different. Say, for example, you are coming to here following a specific route, and maybe when you are attending the class every day, you are doing that. But say in the evening time when you are coming for a coffee, you may decide that we every day go through this route, let's go through the jungle and explore a new route. So it is somehow inherent in the nature of human. And that's why when we will discuss about reinforcement learning, as I told during the introduction, that often this is investigated by human psychologists, you will see that we also bring some of this human nature into the agent, that even the agent is very accustomed to doing something, it will explore. The exploration can be wrong, but there is also we will investigate the possibility that this exploration will give me a better possibility. And there will be some very different terminologies, like we already come across these terms in the context of value and policy iteration algorithm, like reward is the short-term benefit, utility is the long-term reward, or in value and policy iteration algorithms, we learn utility from the reward. Then the policy will tell at any state what is the best action to do. And then the state action mapping as the state transition probability matrix. And during Q learning also, you will see that we will define the Q function as a functional on this state and action, or state and action pair will work as the independent variable. So these terms, we already accustomed with some of these terms during value and policy iteration or Markov decision process lecture, but we will utter these terms, which are a bit different than we used in supervised or unsupervised learning, where we mostly talk about training data, feature validation, etc. So this is the basic context, and you will find it's very similar to the what we learned in the MDP class, that there will be a set of states. The state can be, in case of motion planning, that the Euclidean position of the bot. Later on, we will also add the orientation or all the 6 DOF of the bot. So for example, if we do reinforcement learning for a fixed-based robot, many times it's the end effector position is not only important, but its orientation is also important for task execution. When we are doing a game, then we will encode a particular arrangement of pieces on the board as the state. And a set of actions that what is allowed to do in terms of movement. And in all subsequent cases, we will assume that the set of actions is very limited. Only there are a 2 DOF system. There are 4 actions possible. But then I showed you a case study where we worked with 8 actions, and you can also increase the number of actions when you will actually implement. We only consider 4 actions because it will be easier for us to hand calculate or explain. Then we will talk about the state transition probability matrix. So just to reiterate, this matrix will tell the probability of reaching state S dash when the agent execute action A at state S. So when we learn these BFS, DFS, S-star sort of algorithms, we assume that it will be deterministic, that if the agent decides to go from one state to other, it will the output of the action will be certain. But in this case of reinforcement learning, or just like our previous value or policy iteration algorithm, we will consider a probabilistic agent, that there will be a non-zero probability that if the agent execute or tries to execute action A at state S, it may not be reach state S dash, it will reach a different state. And then there will be a reward function. So in the most cases, we represent also the reward function as in some of the formulation, you will see that we will represent the reward function as RS. And in some formulation, we also put the A and S dash with the reward function, that what is the reward if the action, like the state transition probability matrix. It has a good advantage that I can use the similar matrix structure to store the reward also. But in some formulation, you will see the reward is only expressed as RS. And the discount factor gamma. So we come across this during the value iteration algorithm. So it's a value between 0 and 1. It can be make 1, but then it will be a complete additive function. So we'll go into, we discussed about the discount factor very briefly during the value iteration lecture. We will further see the effect of gamma in subsequent algorithm. Now, the main difference from the value and policy iteration algorithm is that we do not know the model. Okay, this is unknown to us. So in value and policy iteration algorithm, we assume that we know the model. So you may ask that how do we make the assumptions? But here we will learn that how we can estimate that model. And in many reinforcement learning algorithms, especially the model-based algorithm, you will see the whole algorithm is centered around to learning this model. And once I learn this model, then I will go to value or policy iteration algorithm to find the best policy. And yes, of course, the output of the reinforcement learning will be finding the policy that if I am a state, or if say you are in a particular place in Bangalore city, you know that what to do to reach IISc, something like that. So this will be the setup. So I took it again from the Russell Novick book, and you can follow that. And this is the same setup we used during our MDP lecture on explaining value and policy iteration. That is a 3x4 grid. There, the +1 is a goal state, which is good. -1 is also a terminal state. Both +1 and -1 are terminal state, where if the agent reaches such a state, we consider that this is the end of the epoch or end of movement. And +1 means it's good, -1 it's bad. And the gray color box is not reachable. So you can imagine that this is a pillar in the middle of the room, like that. And the Markov property is, again, please take a note of this Markov property, that the transition probability depends on state only, not on the path to the state. Okay, this is the Markov assumption. And in this lecture, we will not talk about POMDP. So we'll assume that the agent knows where it is at when it is moving. And in terms of action, we will consider the same thing, that if it chose an action, it has 80% probability to follow that action, which is marked here. There are only 4 possible actions, but there is 0.2 probability it will go perpendicular, 0.1 left, 0.1 right. So this assumption we used for the explaining the MDP. But in this case, the difference will be that in the subsequent algorithms, we will consider that we do not know this model. Okay, so we have to learn these values. So next, we will discuss 2 types of approaches to RL. One is the model-based approach, and now I think it's obvious to you that we will try to learn the MDP model here, like the state transition probability matrix, and then we will use the policy evaluation to find the optimal policy. And we will learn 2 algorithms, which is trying to do that in slightly 2 different ways. But then it may happen that the state space is very big, or I do not know the full state space, and then it may not be worthy to know the model for the full state space. I can learn it where we belong to. Like, say, for example, for traveling within Bangalore, you need not to know the or remember all the road structure in the whole India. You can only learn locally in your neighborhood in Bangalore. So these model-free approaches will be that we will try to derive the optimal policy without explicitly learning the state transition probability matrix or the full model. And of course, it's useful when, as I explained, that when the model is difficult to represent and or learn. And this model-free approach, we will learn 2 algorithms. The first will be the temporal difference learning, and then we will learn the Q learning. There will be another type of classification, passive versus active learning. In the passive learning, it will be like that the agent will observe the world and it will get a set of training samples. Each training sample will term it as an epoch. What is the training sample? That the agent, as if it's roaming around the environment, and till it is reaching a terminal state. The terminal state can be either good +1 or bad -1. And it will look at this examples of training data. So here you can find the resemblance to the supervised learning. And then it will analyze these training samples and try to learn the model, or it will learn the neighborhood where it is roaming. But it will not act on the environment when it is learning. So first it will learn, then it will act. In case active learning, the agent will learn as it is acting. So it will learn as it is moving and acting on the environment. So in case of passive learning, we will learn this direct utility estimation, adaptive dynamic programming, and temporal difference learning. All three will be passive learning techniques, as you saw in a previous slide. And the Q learning will be an active learning algorithm, which will also be deriving from the temporal difference learning, that where the model will learn as it is going. And you can readily see the advantage of that, that you need not to collect training sample or wait till you collect adequate sample. You can, as soon as you make your robot and it is ready to move, you can execute that algorithm and learn on the go. So first we will talk about the passive reinforcement learning algorithms, because the active learning algorithms will be built up on the concept of the passive reinforcement learning algorithm. And when we discuss the passive reinforcement learning algorithm, we will again use this grid structure and we will assume that the agent is just following this policy. Just assume that somehow it initialize the policy with these values. And the difference from, again, it's maybe a bit of reiteration, that we do not know this state transition probability matrix. Okay, so that will be the difference from the value or policy iteration discussion that we have. So how we will generate training sequence? So for the model-based learning, first we will talk about model-based learning, then we will go to the model-free learning, that we will learn the model empirically through experience, which means that we will let the model agent to experience the environment. What is by experience? That it will move through the environment, it will get some rewards. Initially, it will not get reward. It will get, once it reaches the terminal state, then it will get some reward. And then we will back calculate. And from that, we will try to learn this utility or the state transition probability matrix. And here I put the Bellman update, because just remember it from the policy iteration discussion. So just to explain that this is our state transition probability matrix. This is the policy, and for policy iteration, we randomly initialize the policy, and this will be the reward, and this is the discount factor, and this is the how we update the utilities on each iterations. And as we saw in the policy iteration, just to remind you that we find this equation for all possible state, and then we solve it like a set of linear equations. So let us see how we can do that. So this is an example that where we got some training sequence. How? Let us do a, I will just use a different color to make it. So just imagine the agent is experiencing environment, and in all cases, it's starting from this 1, 1. So in the first case, it's from 1, 1, it is reaching to 1, 2 here. So just 1 second, I will use slightly. Yeah. It is going there, and then it is going 1, 3. Then it is going to 1, 3. Then it is coming back to 1, 2. This is the uncertainty. Again, going back to 1, 3. So basically, it's doing a loop here and here. Then it is going to 2, 3, 3, 3 and reaching the goal state here. So next, this is one epoch. This is another epoch. It's starting from 1, 1, sorry, 1 to 1, 2. Then it is going to 1, 3, 2, 3, 3, 3. And then it is, instead of going, it's coming back to 3, 2. Then again, it is going to 3, 3 and 3, 4. Okay, so this is another iteration. And the last iteration is something like that, that it is going this way, then this way, and ending up here and getting this -1 reward. So say for the simplicity, we will consider only these 3 values. Next, what we will do, that here you can see that I just wrote these training samples, these 3 training samples in some bigger font. And just remember that we initialize the reward at a minus 0.4 value. And as I discussed in the previous case, that we will have a more detailed discussion that what happens if we do not initialize the reward at minus 0.4. But for the time being, just consider that the reward values are initialized at minus 0.4 for all non-terminal states. The +1, -1 are the terminal states. Okay. Now let us see what I can do, that we are getting this +1 here. So I can write that I am getting 0.96 here, 1 minus 0.94. So I am just not writing the 0 point here. So we are getting 0.92 here, 0.88 here, and similarly 0.84 and so on. For this, I can again get 0.96 here, then 0.92 here, 0.88 here. And so for the last epoch, we can write the delayed reward or utility like -1.04 or -1.04. And then we can make a table where we can list these state or these delayed reward or utilities. And you may see that there is some repetition of visiting, that this 1213, 1213 is happening twice. So you will get same values multiple times. But we can put all these values in a table, and then it becomes a supervised learning problem that we can feed it to a neural network or any other supervised learning problem, where we will try to reduce the error and try to converge to a set of values of the utilities. So exactly this is done in this direct estimation, where we directly try to estimate the utility. And when they are the rewards are repetitive, that means same reward we are getting for the same state multiple times, so you can average that. So this may sound very intuitive and easy to do, that we have to just go through the training samples or epochs and list the delayed rewards and feed it to a supervised learning problem. And later on, you will see a similar approach when we will discuss the deep Q learning. But this is not the best approach. But and it is very intuitive also. But it does have a problem, that it is not exploiting this Bellman constraint. So in more physical term, what it means, that by putting the utilities values directly to a machine learning supervised learning agent, we are assuming that the utility values are independent to each other. So often when we do statistical analysis, we do it, we collect data and put it in a statistical package. So supervised learning is also a statistical, it makes the similar assumptions that the samples are independent to each other. But in this case, that is not. What I mean by that, that the utility of, say, this state, it also depends on the utilities of the previous states. So by directly estimating the utilities through a supervised learning agent, we are not making these wrong assumptions that the utilities are independent to each other. And we are not using this Bellman constraint. So in the next approach, how we can incorporate the Bellman constraint, in the adaptive dynamic programming, what we do, that we create such a similar table from the training sample, but we prepare the table something like this, or we try to populate. I am just marking it as R-dashed, which is the utility or the delayed reward, what we got here, these values. So in this case, we are putting this value directly against the utilities, But in the adaptive dynamic programming, what I will do, I will put this delayed award with respect to this table. Let's say if I look here, say this is 1, 1, then up action will take it to 1, 2. So I will prepare the table like this, that this is say our state 1, 1. I am going to 1, 2. And I am doing an up action. What is the delayed reward here? In terms of probability, we can, it is something like that, this P S dash given S and A. So we are trying to find this probability, that what is the probability of reaching the state S dash given state S and particular action. Basically, that is the transition probability matrix. And we try to learn this transition. Okay. And yeah, it is simply the fraction of times we see S dash after taking A in state S. Both are same expression. And from that, we put it in the Bellman-Ford update, that once we know the state transition probability matrix, we can use value or policy iteration. So in this case, we use the policy iteration algorithm to get the optimal policy. Problem with this approach is that we have to learn the state transition probability matrix for the whole state space. So in this particular example where we have a 3x4 grid, that is fine. But if it is like a chase or a practical example where you are flying a drone or moving a robot for a slightly larger workspace, learning the full state space becomes very difficult or sometimes impossible. For example, this backgammon game have 10 to the power 50 equation in 10 to the power 50 variables. So many states are there. So what we can do now, the adaptive dynamic programming has a very good advantage over direct utility estimation. So in direct utility estimation, the utility values converge. Converge means they have same values after a lot of training samples, a lot of iterations. In adaptive dynamic programming, since we are learning the state transition probability matrix and using the policy evaluation for smaller state space, if we can do that, we can get convergence very quickly. And you will see the comparative graph very soon in the upcoming slide. But the main problem is learning the state transition probability matrix for the full state space. So an intermediate solution is that we will only learn this state transition probability for our locality or where we are moving. What we define by locality, that we will look at the differences of utilities, like say from one iteration in another iteration, how the utility is changing, or when we are reaching the terminal state, we can back calculate the utilities of the neighborhood. And what we will try to do, that we will not try to learn the utilities values for the whole state space, but for our neighborhood, we will try to bring the unknown utilities to these best values, what we assume or what we can get indication from the terminal state. So we will only work on the localities. How we do that, and here also we still consider that there is we will initialize the policy will still be fixed, that how we do it mathematically. So here you can see this is the previous state, and sorry, I will just turn on the highlighter. So this was the previous state, this is the new state, and this is the policy, and this is the action, the arrows. Okay. So what we will do, that we will update the utility based on this sample change, that we are just changing one action and we are changing this state, and we will update the utility based on the previous utility. So if we look at more, say, a single equation, that this is the new state that I reached after executing this action, like you can consider that S dash state, and this was the previous state UI. So I will update UI based on the utility of the UJ. Now it will make perfect sense if you consider that UJ was the terminal state or +1. So just like in the previous class, if it is +1, you can easily see that I will change the UI to a value so that it has a bigger value, and it will indicate that if I take this particular action at UI, I will reach the terminal state. And similarly, the same principle you can consider this as it iteratively goes down to all other non-terminal state, that based on the action, I will look at the neighborhood and I will try to push the present utilities to the better utility or a desired utility, which will bring to the goal state. Now we talk about this gamma or this learning parameter alpha a few times. So we, in this case, that we will make sure that there can be some cycles you can see that we are circling in the same places. So we can choose the values of alpha or decrease this value for the same state. So if the agent somehow go to the circle and staying in the same state, we will not consider it that much on updating the utility. But when alpha is going to a newer state, we will consider that in our update principle. So this may not be very clear to you right now, that here we will just maintain this table ni, which is the number of times we are frequenting a state. But you can just think that this alpha, what it will do, that if I am revisiting the same state, it will not give me much credit. But if I visiting a new state, it will give me more credit. So somehow this alpha value will encourage exploration over exploitation. And it will be further discussed in the next class when we will discuss about this active reinforcement learning or multi-bandit problem. But presently you consider that in temporal difference learning, that we look at the next state of the utility and modify my present state based on the quality of the next state, and with an aim that I will modify the local utilities to match it our final or desired utility. So this is a comparison of the in the number of epochs, that the number of times we iterate. And here you can see the utility estimation. So in y-axis we put the utility values. So the trade-off is you can look at these values here: 100, 200, 300, 400, and this is 200, 400, 600, 800. So the temporal difference learning require more epochs or iterations to converge than the ADP. But the advantage is for each iteration, TD has much less computation because it is just solving the problem locally with respect to the neighboring states. While the ADP at each iteration, it solves for the full state space. So each iteration is costly for ADP. Each iteration is less costly for temporal difference learning. So if it is a smaller state space, we can go for ADP, where I can take all the state space into memory because it will give me faster convergence. While in case of TD, if the state space is very large, we can go for the temporal difference learning because each iteration will be less costly. But with more training samples, I will converge the utility values which I need for the local neighborhood. And there are some problems with the TD value learning, that it's a model-free way to do policy evaluation because I am not learning the full state transition probability matrix. But we don't want to calculate the value of utility and from the utility value to find the action using the argmax operation. Rather, we directly want to know the action. So that we will learn in the Q learning. And when I will start active learning, we'll again maybe revisit this slide once more. But for the time being, here is the comparison or summary. The direct utility estimation, this is also model free because I am not learning the state transition probability matrix. It is simple to implement. Now we directly estimate the utility by solving a supervised learning problem, but we consider the utilities are independent, which is not true. That's why it does not exploit the Bellman-Ford update and often have slow convergence. Where in ADP, we learn the model, the state transition probability matrix from the sample training data. But it is harder to implement for a bigger state space because we are trying to learn the whole state transition probability matrix. But for smaller state space, it can guarantee a very faster convergence because we are learning the whole environment in the form of the state transition probability matrix. And while the temporal difference learning, it's also model free. So it's only learning the utilities of the neighborhood where my agent is getting samples from. Each iteration, we are just updating the utilities. It has slower convergence that it needs more training sample, but over time, we can solve the problem in a model-free way, exploiting the Bellman-Ford update, unlike the direct utility estimation. So here I will stop the session right now. Everyone. So in the last class, we discussed about introduction to reinforcement learning, how it was different from supervised, unsupervised learning. And also we discussed about 3 different algorithms on passive reinforcement learning, namely this direct utility estimation, in which we estimated the utilities directly from a set of training samples, or called epochs. Then we talked about adaptive dynamic programming, which was a model-based method, and where we try to learn the whole model, which means the state transition probability matrix. And the third one, we discussed about temporal difference learning, in which case we only calculated utilities in the local neighborhood without solving the whole state space. And we showed that although it takes longer time to convert to ADP, but still it converges for a set of utilities. And it is advantageous in cases that where the state space is very large, or we do not know the full. So we discussed this, compared also these 3 algorithms, and temporal difference learning is also a model-free method because we are not learning the full model. Now, in that background, today we'll discuss on active reinforcement learning. And the main difference with passive reinforcement learning is that here you can see on the left side, I also put this picture, that from the policy iteration lecture, we started talking about that we will assume a policy, and based on that, we will refine that policy. So in all the passive reinforcement learning algorithm, we assume this arrow marks, which assumes a fixed policy. And based on this fixed policy, we calculated the epochs or training sequence. Based on that, we calculated utilities, or we learned the state transition probability matrix. And from that, we again run another policy iteration algorithm or something. And maybe we calculated a better policy, or we claim that that is an optimal policy. In contrast to that, in active agent, or in active reinforcement learning, it will as if go back to our value iteration algorithm. That remember the difference between policy iteration and value iteration algorithm. In value iteration algorithm, at each state we evaluate or calculated the maximum expected utility for all possible action, and chose the action which is maximizing the expected utility. So similarly, in the active agent, we'll require the outcome probabilities of all actions instead of assuming a fixed policy. And that way, the active agent explores the world. That means it does not decide a fixed policy. But then there is trade-off between exploration and exploitation. Exploitation means that it will keep on doing the thing which it was doing before, and exploration means it will go to newer states. So here we may sound a bit philosophical because it's very similar to what we do in our regular life also. And of course, these are also true, but it's a bit philosophical, that sticking to only known world ensures stability, that it will take you to the goal state, while exploring new opportunities may improve the possibility of present situation. And also comically, we know this statement, curiosity killed the cat. So there is always a probability that exploration may lead to a worse situation, but still it's worth to take the risk that if exploration can lead to the agent to a better way to achieve the goal state. Okay, so let's see how we do that. So this is our previous example. So the utility values are not written here, but you can assume that it was the previous example that we worked on. And this is the problem with the optimal policy of an ADP agent. So what happened that the ADP calculated the whole state transition probability matrix from a set of epochs. After it calculated the state transition probability matrix, it found an optimal policy which takes you to the goal state following this path. Okay. Now it turns out to be, and here I am not showing you why because the utility values are not written, but just agree with that calculating the utilities, it can be found that it can reach the goal state in a better way. And here comes the dilemma that in one case we are telling the policy iteration algorithm is giving me optimal policy, but on the other hand, I am telling that no, it is not giving me the optimal policy. Then what is the catch? Because it sounds like a uh, self-contradictory statement. That one case we are telling that the algorithm is optimal result, but then we are telling that no, it is not giving the optimal path. So before explaining that, let me show you this. I kept on telling a few times during from the beginning when we started the Markov decision process lecture that in all these example, we assume that we are initializing the initial reward at minus 0.04. What if I initialize the different values? So on the left hand side, you can see, sorry, that this is the policy we get when we assume r equal to minus 0.04. But these are alternative policy we get, especially in this case, you can see that I don't have any possible action in this state. Value of r is chosen greater than 0. And as you may now assume that this is something, whenever we write AI algorithms, we make something called closed world assumption, which means the agent only knows, percepts, allowed it to perceive. So here, when we are talking about optimal policy, etc., everything we are telling with respect to a model. So what do we mean a model here? That in the left-hand side, why I get this blue optimal policy, why it is optimal? Because it is optimal with respect to the training samples or the models that I learned based on the initialized fixed policy. And on the right-hand side, you can see that how the initialization of the initial reward can change this policy. So the agent is not learning the true environment. It is sensing the true environment through a set of training sequences. These training sequences are dependent on the initialized fixed policy. And based on that, we are claiming optimality. But that may not be truly optimal with respect to the true environment. But then we may ask that why don't we learn the true environment? Because that is the problem, because many times we do not know the true environment. We only sense the environment with a set of sensors or some other means by exploring the environment, etc. So how we can explore the environment? So mathematically, in our everyday life, what we do, that although we know that there is to reaching in the class, so when you are coming to the class in morning from your hostels, you will stick to your known path. But say if you went out for a casual walk with your friends, you may explore maybe the going through the forest route or trying to find a shortcut. It may happen that you will find that there is a shortcut, but you cannot take your bicycle or bike through that route. But still you will explore that. Maybe sometimes you can have a walk on that, even though that is not drivable. So how we do it in our everyday life, I mean, that's what makes us a human being or exploratory being. How we can do it mathematically. So here we will define this new function, this NAS, and we briefly talk about this in one of the algorithms before, that it will make a log that how many times a specific action is executed at state S. And why so? Because at always in a say known state, if I am taking the known action, that will be some sort of exploitation, that I know that I did it before, so I will keep on doing the same. But the exploration tells that in the known state also, let us explore something different. So we will define the second function, this exploration function, which will encourage taking curiosity. So this is something again reads a bit philosophical. Greed is traded off with curiosity. So do not take the word greed as a bad sense. So greed is something like that I will define this threshold value any. So maybe I will take the known action as a threshold number of times. But beyond that, if I am coming back in the same state, I will explore something new. And this function allows me to do that. So it's kind of physical resemblance is something like that it often happens in a forest or desert, or even some things in a very thick urban area, that you are thinking you are going to new place, but after some time you are finding that you are coming back in the same place. So in older days, explorers, what they do, that they left some marking on a tree trunk or some sort of marker somewhere to make sure that they are not coming back at the same state. So something similar here, that if the system find that you are coming to the same state multiple times, it will put a threshold on your action. It will tell that you do not take the same action, even though you believe that this action is taking to your goal state. Rather, you take an alternative action. So ensures that each state action pair will be tried at least any time, so where any is our threshold. After that, it will encourage to explore new. So we already seen the problem with the ADP agent, that one problem we already discussed multiple times, that it has to learn the whole state space, which is difficult. Second problem we found that it's getting the optimal policy with respect to the training epochs. Now in TD, we try temporal difference learning. We solve the first problem, that we only learn at the local neighborhood. But again, in the temporal difference learning also, we learn the utilities. And then we need one step look ahead, that from the utility, we have to use this argmax formula, just like our value iteration algorithm, to find the action. Because utility is only a tool which is leading to me a appropriate action, which I can execute to make to the near to the goal state. So here we define a new function, this Q function, which is conditional on both the state and action. And just we do the temporal difference with respect to this Q value, that here I am already getting the action. So let us see what this Q value does. So we define this new function Q, which is conditional on both state and action. And the relation to this utility is exactly same. This our value iteration algorithm, what we do, that the utility can be calculated, that whatever action is maximizing the Q value at a particular state. Then we set up this constraint equation for equilibrium, that how we learning the new Q values. And you will find that this is exactly similar to the value iteration algorithm, that at any point I am taking the maximum value, which is maximizing my action, multiplying that with the probability, and I am summing them up and adding this discount factor. Now, the problem is I do not know this, this state transition probability. This I do not know, because if I already knew that, I can just do policy or value iteration. So then what we do from ADP to temporal difference learning, that instead of this learning the whole model, I just update it based on the local neighborhood. Okay, this U pi S dash, where pi was the fixed policy, because that was the passive learning. So this was the temporal difference update for utility. And since we take this difference, that's why the name comes temporal difference. So now what I will do, I will just follow the same equation that we do for temporal difference, but instead of this U, I will use the Q. And you can, I put them one below other, and you will see that here what I did is that I get rid of this pi term here, because this pi was fixing the policy. So I do not have any fixed policy here, rather I am exploring for all action here. And then I do not need this state transition probability matrix. I am just solving it for the local neighborhood where the action I am taking. And what is Q? Now, I think it will make more sense. The Q is just telling you the quality of an action. That you can see here on the second line, second bullet point, that Q is, the utility is the max action or the max A value, or max A, or the best action in the possible state. So Q stands for quality. So now if I again look back this full equation by explaining each of the individual term, it looks like this, where this RT is the reward. So this screenshot I took from Wikipedia, or a few days before in Wikipedia, because it keeps on changing, but I think this is very standard and well explained. So here you can see the explanation of each term. This is the current value, no confusion on that. This is the learning rate, just like our supervised learning agents. This is the reward on the state T, discount factor, like this Bellman-Ford update or value iteration algorithm. This is the value that which is maximizing or estimate the optimal future value. And this is the current value. And this whole term is the temporal difference, that I am discounting this using gamma. And then I am adding the reward of the present state to keep it within limit, and the learning rate further helping me to tune the speed of learning, just like in supervised learning. And an episode of the algorithm ends, so in the state ST plus 1 is the final or terminal state. So now if I write this whole equation algorithmically, and just here you can see that if I just redo this assign these terms, or alter this term. For example, 1 minus alpha into QST is the current value weighted by 1 minus the learning rate that I am taking forward to the next state. And alpha T is the reward, again multiplied by the learning rate, and alpha gamma max QST, the maximum reward that I can get in the neighboring state. So I kind of poke the neighboring state and see which is giving me the maximum reward, and based on that I make a move. So here I am exploring the all possible action instead of the based on a single policy, as we are doing with the passive learning. So this is the algorithm Q learning implementation. So this equation, you will see that this is exactly same that we had in the previous slide. Only a difference here, what we got is this term. So this term, as we explained in 2 slides before, that this is somehow tuning the exploration, or how much we will explore, or kind of doing a balance between exploration and exploitation. So we are multiplying this whole temporal difference by this term here. So I will just get the laser pointer. 1 second. Yeah. So this is somehow getting multiplied to this whole temporal difference here, like the learning rate. And so as the value increases, that even though action was maximizing the Q value, but that will be discounted more than an unexplored action. Okay. And once we know that we will, and the terminal will be that when S is a terminal state. Okay. And these are the stopping condition. If S is not null, that if there is, the agent does not explode all possible state, it will keep on doing that. So now the question is how much we will explore. Is there is a optimal exploration strategy? It turns out that this is become a very difficult problem. So under certain assumptions, we can use this Gittins index where we assume that the rewards are independent to each other. We can find that as an optimal exploration for a multi-arm bandit problem. So the multi-arm bandit I will come in a second in the next slide. And then there are these greedy in the limit of infinite exploration, or this GLI principle, that it leads to optimal exploration, but although it is difficult to prove, that it can be proved under assumption of certain independence assumption. So this paper, I just put a snapshot here. So if any of you are going into the details of multi-arm bandit or active reinforcement learning, you can check it out, that how we can come to this Gittins index. But when we are discussing this multi-arm bandit, we will rather go into the detail of the multi-arm bandit problem. So this bandit problem is very well known, and of course it's coming from this casino and Las Vegas culture, where you will have a set of machines where you can pull a handle, and with some probability you will get a reward. So it already exists in many places. And as a good gambler, what you try to do, that you will choose the machine which has the maximum expected utility to give you reward. So before going into the mathematical details of the bandit problem, let us me show you one quick video of using it in a practical motion planning or robotics situation. So the videos in a much better form with all subtitle voiceover is available on YouTube. But I will just show you the clip of the video which is relevant for the present lecture. Little bit of context, that we set up this virtual warehouse in our lab. So on the top right corner, you can see a mobile robot. So this is a Burger bot, which is people use it for standard motion planning algorithm. And what we do, that using a mixed reality headset, we created some holograms where in this empty floor, we set up a set of crates, etc., as if it's a occupied warehouse floor. And the robot is trying to reach to this fixed base bot, which will serve it. And the robot also recognize these virtual objects as physical obstacles. So it's avoid both physical obstacle, as you see in the top left corner, and virtual obstacle. And there are multiple fixed base bot. So each of the fixed base bot as if like one of the bandita, and it will taking the payload to the fixed base arm for servicing. Another analogy may be that there is a bunch of cars and there is a fixed number of service stations. So the cars are being distributed to the service station following various optimality criteria. So this is the basic implementation, and where it that next what Ajay worked on, that what if there are multiple agents and also there are n number of service stations. So how we can optimize the distribution. Second, how this distribution or the task scheduling among the bots changes between humans and an automated agent. So for automated agent, try to optimize it, which will reduce the, say, the service duration. While for humans, when we ask them to take the robot to the reward station and they will get some virtual reward, we find that the humans not only cares about reward, but they also cares about the distance they have to travel. In the next class, Ajay will discuss it into further detail. But for the time being, what we will do, or what we will take away from this video, that we will have a fixed set of service stations. So this is the formulation or mathematical formulation of the k-arm bandit problem. Imagine that I have k number of arm, k is a finite number, and each arm is giving you a reward in some random distribution with, say, mean of mu and some standard deviation of sigma. And we do not know this mu and sigma. How we can know that? That which every time I am pulling the lever, it is giving me an indication to this underlying distribution. So each lever pool is similar to the state transition or training epochs in our previous set of algorithms. And of course, if I do not get reward, I will get loss. And we will, with probability 1 minus mu a. And what we will learn in the bandit problem, how to pull this and what sequence we should pull the levers to maximize the total reward. So with respect to our previous example, that each fixed base robot or service station was a bandit and each mobile robot is an arm, and we have to allocate this mobile robot to the fixed base bot, which will maximize this winning probability. Now, what is the reward? So in our experiment, we put some virtual reward with respect to each reward station, but in reality, the reward will be minimizing the service delay, maybe the minimizing the waiting time, maximizing the maximizing the, say, the profit for each service station, if service station is associated with some profit value like some virtual reward like that. So you can set up the reward based on your requirement. Next, there is much easier to now explain this principle of exploration and exploitation. So previously we had discussed classing exploration versus exploitation, that you are in a physical state S, and which action you will take, which will maximize your profit in terms of getting this utility reward value. But here, your exploration will be that you will pull an arm which you have not pulled before, and exploitation will be, say, somehow you know that that guy got a reward from that arm, so let me try my luck with that arm only because I saw that someone got a reward from that arm. So exploration, that pull an arm we never pulled before, and exploitation will be that pull an arm A, which we currently have the highest estimation of mu A. And then we, this is the setting, that set of k choices. Each choice A is tied with a probability distribution PA, which I do not know. And each time or each round, I am pulling a lever, that is one round. Earlier, we are talking about state transition probability. And we win reward XT drawn from PT. And our goal is to maximize this expected probability over a sequence of P pools. And what we don't know is the mu A for each term, that what is the underlying probability distribution of each term. So next, how we can maximize this term. Okay. So the most basic algorithm here is the epsilon greedy policy. So if it has some resemblance with the simulated annealing algorithm we discussed during our state space search algorithm. So we discussed this simulated annealing in terms of this eye tracking, I guess, controlled head-up display. There is some similarity, we'll see quickly. So, but the algorithm is super easy to explain or understand, that at each time step, the agent selects an action, that at each time step, a lever will be pulled. The agent follows the greedy strategy, that it will pull a lever which it has earlier pulled with a probability 1 minus epsilon, and the agent selects a random action with probability epsilon. So you are, say, as if you are tossing a coin. If it is head, you will pull an unknown lever. If it is tail, you will look at the existing lever and you will choose the one which was maximizing your expected probability, which you are, say, already calculating or tracking, looking at other people's. So it can be proven that for suitable choice of epsilon t, so when you are tossing a fair coin, epsilon t will be 0.5, that we have a time complexity of k log t, where k is the number of the arm and log t is the number of round. And with probability epsilon t, we are exploring, and 1 minus epsilon t, we are exploiting. So although this algorithm is super easy and easy to implement, but it does have, so it is something like this similar principle. I just put it here, that where alpha was our learning rate, that we are choosing the new Q value, where 1 minus alpha, I am still dragging the old value, that what we presently have. And later on, we saw that we are multiplying this alpha with this function NAS, which is doing the job of the epsilon in the Q-learning implementation. So there are some issues with epsilon greedy. One is something, again, sounds a bit philosophical, that it is not elegant in the same that algorithm explicitly distinguish between exploration and exploitation. And exploration makes suboptimal choices, that I have a choice of arms which I did not explore before. So which arm I should go for? Should I randomly pick one arm? So epsilon greedy tell that you randomly pick a bar which you have not explored before. Can we do something different? So there is a principle based on this confidence interval that we will compare the arms during exploration or exploitation based on the confidence interval that when they gave me a reward. So in this lecture, I will not go into the details of the confidence interval right now. Rather, in the next lecture, we will go into detail onto this, that how we use the confidence interval and how we implement a multi-arm bandit-based task scheduling approach. But instead, now we will move to some more advanced reinforcement learning topic. And of course, one very popular one, I think it's well used by Google DeepMind, this deep Q learning network. So again, you can remember the direct utility estimation where we told that I will make a table of utility values and with respect to the state values, and then we can put a supervised learning agent to learn that. Something similar, that we will create a table of Q values, and then we will have a supervised learning agent to learn the Q values. And when I have a sufficiently bigger state space, I will have many such samples. There are some problems that here when we do many statistical processing, and as I told, the difference between direct utility estimation and ADP, that we told that in direct utility estimation, we do not exploit the Bellman-Ford update, which means that we consider the utility values are independent of each other, which is not, because the utility of the next state depends on the previous state, which is expressed by the Bellman-Ford update. Similar problem also happens in DeepQ network, that where the independence assumption may not hold true, and there are way of using convolution neural network for calculating the deep Q values, and also there are some double Q network, etc. But the basic takeaway points, you can see that we will have a table of Q values, and then we will use a supervised learning agent, an appropriate agent based on our field, for learning the Q values. And another interesting reinforcement learning algorithm is the inverse reinforcement learning. So in all this reinforcement learning, what we do, that we initialize some reward values. So in passive learning, we learn that we will have a fixed policy. Active learning, we are not doing fixed policy, but still we have a RT in the term. RT has to be initialized with some values at the beginning of the algorithm. In inverse reinforcement learning, what we do, that we collect a set of samples, which I can easily do, where you can see some resemblance with the passive learning agent. But then from these samples, we try to learn the reward distribution. So for example, I collected the traffic data of Bangalore or New York. There is something called New York taxi data set. And from that, I saw that over during a specific time period, maybe in the midday period, where I am getting the more traffic or more traffic jam. And based on that, I can learn a reward structure based on the traffic density of the city. So we exactly that. So here you can see one example again, that we learned some reward distribution, giving some examples to this fixed base bot. And then without using any computer vision, it learned to avoid this physical bars here. So we gave it sample using the holograms, that we give it some sample trajectories. From the sample trajectories, it learned the underlying reward distribution. And then when we replace these holograms using physical sticks, it actually retains this knowledge and it is not hitting those physical ones. So then we extend it for mass, and we hand trajectory in a mixed reality environment, as you can see. And from that, we learned a 3D reward distribution. And from that, we compare different reinforcement learning algorithm. This will further be discussed in further detail in a future lecture. And we use this inverse reinforcement learning on predicting finger movement in a 3D environment. So see a video. So again, I will just
This work presents comparison of target prediction in virtual and mixed reality environment using inverse reinforcement learning. In reinforcement learning, manually tweaking of rewards is necessary until the desired behavior is observed. Therefore, a better way is to learn the rewards by observing expert. Thus, IRL learns the underlying reward distribution using expert demonstrations. Expert policy and transition probability is given or obtained from expert demonstrations using methods such as supervised learning. IRL is then implemented to learn the reward distribution. For a robotic agent in autonomous navigation, it is easier to estimate the initial policy and transition matrix. Whereas it is difficult to estimate the same for hand motion during a pointing task which has high uncertainty. To overcome this, sampling-based approaches is recently being used to obtain reward distribution using IRL for tasks with high uncertainty. Video of target prediction using sampling-based IRL is shown. Green is the actual target that is to be selected. OptiTrack motion capture system tracks the finger coordinates. After a certain length, tracking stops and the predicted target is represented by increase in size and blue color. Reset button resets the entire system to initial settings. On clicking the red ball, tracking starts again. Sometimes, the algorithm predicts more than one target when the reward for multiple targets nearly matches the total reward of the partial pointing trajectory.
Stop recording.
We implement a sampling-based maximum entropy inverse reinforcement learning (SMEIRL).
Stop recording.
Expert dataset was collected and pre-processed to extract expert features. A sampler was used to generate sample dataset from which sample features were extracted. SMEIRL was then implemented using these features to get optimal reward weights which were used for target prediction. Lower feature deviation metric and mean Euclidean distance error shows the accuracy of the learned reward weights using SMEIRL. For the initial 55% of the pointing task where most algorithms perform poorly, SMEIRL achieves high prediction accuracy up to 60%. Quadratic extrapolation performs better thereafter. At 30% of the pointing task, SMEIRL achieves 32.6% accuracy in virtual reality and 34.48% in mixed reality. At 70% of the task, it reports an accuracy of 88.21% in virtual reality and 90.37% in mixed reality. It is also observed that target prediction accuracy in mixed reality is higher than in VR using all the three methods. Thank you.
So in summary, what we learned in the last 2 weeks lecture, that our introduction to reinforcement learning, that how it is different from supervised and unsupervised learning, and we classified them based on passive and active. Passive ones need fixed policy, and we learned 3 different algorithms: direct utility estimation, ADP, and temporal difference learning. In active reinforcement learning, we explore all possible actions. The most popular one is the Q learning, and we also learned the formulation of the Martian bandit one. And then we learn model-based versus model-free. So among our examples, only the adaptive dynamic programming was model-based, while the others were model-free. So only one advantage of model-based learning is that if the state space is small, the model-based algorithm ensures as a much faster convergence, or we can get the reward values more quickly, but we also learned that it may not give you optimal policy if the training examples are not exhaustive, because the ADP works based on a. Then we learned the concept of temporal difference and Q learning, that we oddly learn the Q values in the local neighborhood. And unlike the direct utility estimation, here we also take care of the dependence on the states in the form of this Bellman-Ford update. We learned the multi-arm bandit, the difference between exploration and exploitation, that when we will keep on using the arms which we saw to give us reward, compared to that when we will explore an arm which used before. And we just very briefly introduce some topics like deep Q network and inverse reinforcement learning. Of course, we will have a whole lecture on inverse reinforcement learning and multi-arm bandit in the coming days. So after this lecture, I hope that you will have the basic understanding of reinforcement learning, that how it is different from the supervised and unsupervised learning. And later on, we will have some laboratory examples that where we will try to use some of these reinforcement learning algorithms ourselves. So with that, I will stop talking and also stop recording.